did I put in my, like when I assigned this?
You said that the Cartman cycle was reversible.
Okay, yes, that's important. And by the way, it's pronounced Carnot, like a French guy. Um, but it's a very famous power cycle. I said that, so a Carnot power cycle is one that allows you to do a good bit of math to figure out stuff about reversible power cycles. Remember, I said that the efficiency, the performance of any reversible power cycle is the same. Remember? So that means that if we can do careful math for any reversible power cycle, we know the performance of any power cycle. So that's the reason that having one that lends itself to mathematical analysis is really useful. So this Carnot power cycle, we're not going to talk about what it is specifically, but it just goes through a specific set of steps to produce work. And one of those steps is an isothermal expansion. So isothermal means that the temperature stays constant. And it's air. So we're going to assume that this is an ideal gas. Um, and okay, two steps in this cycle are an isothermal expansion and an isothermal compression. Um, and it gives you pressures at the beginning and end of one of those. At the compression, we're going to assume ideal gas. We're given the CP value. And so we want to calculate the pressures at the beginning and end of the isothermal expansion. Well, we just went through the TDS equations. For an ideal gas. And we learned that the change in specific entropy is equal to Cp times the natural log of T2 over T1 minus R times the natural log of P2 over P1. And then we had the other one that said the change in specific entropy is equal to Cv times the natural log of T2 over T1 plus our natural log of V2 over V1. We're trying to figure out stuff about pressure, and we're given a value for Cp, which makes it seem like this is probably the one that we're interested in. And okay, so we're talking about, so we want to know the pressures at the beginning and end of the expansion. So for A, we're talking about this expansion. And so at the start of the expansion, we have so the isothermal expansion is at a temperature of 1400 K. That's the temperature at the end also. Um, and we're given the pressures at the beginning and end of the compression. Uh, so that doesn't say anything about the. Okay, so let's see. So that doesn't say anything about the pressures for the expansion. Um, we know that the change in. Okay, this is a tough one without giving you more information. I believe there are two other stages in this cycle, and I think that they are both isentropic. So I think that the entropy doesn't change. Oh, no heat transfer. Okay, so you have these two isothermal things, and then you have these two with no heat transfer. Um, so, okay, there's an isothermal. Let me go back to that. There's an isothermal expansion, an adiabatic expansion, then isothermal and adiabatic compression. So this is constant temperature. Um, then there is an adiabatic expansion. That means no heat transfer. Um, then there is an isothermal compression. So that's constant temperature again. And then an adiabatic compression. No heat transfer. And I think basically where we're going with this is since in between the isothermal compression and the isothermal expansion, the only other process has no heat transfer. And this is an internally reversible cycle. So what do we know about the change in entropy if there's no heat transfer and it's a reversible cycle? You know, think about the definition of entropy. So the change in entropy is the integral of all the heat transfers divided by where they transfer all the way around the boundary uh, for a reversible process. So if there's no heat transfer,
You can factor out T change.
well, I mean, there's no heat transfer, so you can't use this specifically for T. But what you can say is that delta S stays the same. So delta little s stays the same.
Is it the same or is it 0?
Delta, yeah, S stays the same. So delta S is 0. Okay, so what that says is we're given more information about the compression, but we're trying to find stuff out about the expansion. So if we can find the beginning and ending, like if we can find the beginning and ending entropy for the compression, that tells us the beginning and ending entropy of the expansion. So that's basically the idea. It's not very plausible for me to have expected you to go through and find out the. So that's my fault. I didn't tell you anything about the steps of the Carnot cycle. I got to make a note to myself for next year about this problem. But let's go through it. So so we know that the specific entropy at the end of the compression is the specific entropy at the beginning of the expansion. And S at the beginning of the compression is S at the end of the expansion. So, in other words, now in order to find the change in specific entropy for the expansion, we just have to figure out what these are at the two at the beginning and end of the compression, and we have more information about the compression. So for the compression, we know that the change in the specific entropy is equal to 1.05 1.005 times 10 to the third. That's the CP times the natural log of T2 over T1. Those are the same temperature. So that's 350 over 350, which is just going to be 0. The natural log of anything, the natural log of 1 is 0. And then minus the R value for air times the natural log of P2 over P1. And so that's 500 over 100. I think that was kilopascals, but it doesn't matter since this is just a ratio. And so delta S is equal to negative 287 times the natural log of 5. Can someone plug that in? I don't have a calculator with me.
That's negative 461.9.
461.9. And this is in joules per kilogram Kelvin. And so what that means is for the isothermal expansion, because this was for the compression, the change in S is the opposite of this. So 461.9 joules per kilogram Kelvin. And we're trying to figure out the pressures at the beginning and end of the isothermal expansion. Well, we know that we can, so delta S, which is 461.9, is equal to 1.005 times 10 to the third times the natural log of, for the expansion, that's 1400. But that temperature doesn't change, so it's 1400 over 1400 minus 287 times the natural log of P2 over P1. This goes away. And so 461.9 divided by 287 is equal to the natural log of P2 over P1. And so if we take e to both sides, we get e to the power of, can someone divide 461.9 by 287?
Oh, the negative. Where's that go?
I omitted it.
Should we have one?
1.61. Should we have what?
Should we have omitted it?
I should not have, so I put it back in now. And I also, so this is right now. And this is equal to, well, let's see, I'll put this over, I'll multiply both sides by -1 first, and then this is P2 over P1. So we got that ratio of P2 over P1. So now the question is, how do we get one of those pressures?
we have the temperature after the expansion finishes, right?
Yes, we do.
Professor, for those four like expansions and compressions we run down, are
Mhm.
all four of those happening here?
Uh, they're happening in order like this. Um, so we're just interested in this isothermal expansion. Um, and so if we could figure out, so we have the ratio of the ending pressure to the beginning pressure.
For so at the end
Mhm.
of adiabatic expansion and at the start of isothermal compression,
Mhm.
that's 350 Kelvin.
Yes,
Two and
that's
three.
right.
And we have the temperature between 1 and 2.
We do, yeah.
And we do P2 equals 100 kilopascals.
Uh, no, because so we cannot do that because um, those pressures change during the adiabatic stuff. Um, so okay, I do not think that we have enough information here. I mean, if we were given some like a volume somewhere or something, we could kind of work around. But using the ideal gas law or whatever. But I just don't.
Are we supposed to get a property from the table or website?
Yeah, what do we have? Well, we have a temperature, but we don't have a sec. Oh, so we have, but we don't have and we don't have a specific entropy. We just have changes in specific entropy, right? If we had a temperature and we had at a single state a specific entropy, we could do that. But we just have changes in specific entropy. So I think that just keeps being our problem. We don't have one value at a single state. We only have changes. Uh, and that keeps us from using the ideal gas law or whatever. We could find.
What about the definition of entropy, since it's similar reversible? What looking at this, it says change in entropy is equal to Q.
Mhm. So let me think for a second about the ideal gas law. So we know that PV is equal to RT, and so the change in pressure times specific volume is equal to R times the change in temperature. Um, but again, these are just changes. So I'm just gonna call it here. This problem was, it asks you to do stuff that I didn't really prepare you for, and I'm not sure there's enough information here to solve it. Um, so I'm just gonna, so like, let's say for now that it asked for the ratio P2 over P1. So that seems possible to get. We have a value for that. Okay, and then for part B, what's the heat transfer and work? Um, well, we know that um, we have this relationship that says CV is equal to du dt. And so the change in the specific internal energy is equal to CV times the change in the temperature. This is if we're assuming small enough changes in temperature. But the effect of that is that for each isothermal process, there's no change in specific internal energy. And so the first law says that 0 is equal to Q minus W. So Q is equal to W. And so can we figure out, so if we can figure out one of the work or the heat transfer, we can figure out the other one.
For adiabatic, heat transfer is 0, right?
Yeah, but the two that it's asking about are the two isothermal ones. So yes, you are right about that. But the two isothermal ones will have Q and W. Okay, well, what can we say? So let's start with the compression. This is the isothermal compression. At state 1, so the compression is at 350 K. So state 1, the temperature is 350. State 2, the temperature is 350. Then the pressure for the compression, we go from 100 times 10 to the third to 500. That means we can figure out the volumes at both of these. So the volume, so at state 1, we're going to use PV equals RT. So 100 times 10 to the third times V1 is equal to 287 times 350. So can someone give me that V1?
I got like 1.0045.
Okay. And then same thing at state 2. So we have 500 times 10 to the third times V2 is equal to 287 times 350. So what's V2?
Where did we get? Oh, R.
Yeah, that's R. This is air. So that's,
So this is the specific one?
this is the one for air specifically. Yep.
I got 0.002.
0.002. Oh, then one of those, these should only be different by a factor of 5. So one of these is off, I think.
0.2009.
Okay. Okay, so now we have the specific volumes. So anyone have a guess where I'm trying to go with this?
Use them in the second for specific
what I was thinking is I was trying to calculate the work of expansion. We have that specific volume. We have pressures.
What's the mass of the?
Are you supposed to use that as a
I don't think we're given the mass, are we? I mean, but we could give it as we could put mass in there as part of the answer. But so let's see what we got. So we have that. So pressure is equal to 287 times 350 divided by the specific volume. So pressure is equal to, so that is mass times, what's 287 times 350?
2009, I think.
2009. Okay, so,
No, actually, that was
oh, it,
it was I calculated it factored out when I was in multiplications for like 100,450.
100,450 times the mass divided by the extensive volume. So there's pressure as a function of volume. And so the work is the integral from 1.0045 times the mass, that's the extensive volume at state 1, to 0.2009 times the mass. And it's the integral of 100,450 m divided by v dv. And so you can, this is equal to 100,450 m times the natural log of 0.2009 m over 1.0045 m. Those m's cancel. And so can you plug that in for me?
The interval is negative 1.609.
Okay, times m.
No, the natural one
Oh, okay.
was negative 1.6.
Okay.
Negative 161,668.04.
Okay. Times m. So there's the work. And so from this relationship using the first law, we know that that's also Q. And if we did know uh, the the pressures at the start and end of the expansion, we could do the same thing for that. It really is I really think that probably I would have had to give you one single pressure, either the starting or ending pressure for the expansion, for the isothermal expansion. That's what I think is missing from this problem.
Oh.
Then we could have done everything, but instead all we have is a change, and so we don't know any values at a single state. And then the thermal efficiency. The thermal efficiency. The thermal efficiency. So what do we know about? So this is part C for the thermal efficiency.
That's delta S sometimes equal the integral of from last week's lecture.
Mm-hmm. So I was just going to first write, so this is equal to W over QH. The work done yeah, yep. So this is 1 minus QC over QH. And we know that, yes, that's the way to do it, I think. So, so we figured out the heat transfer during the only two processes in this cycle where there is heat transfer. There's no heat transfer during the two adiabatic processes. So that means that during the isothermal expansion, that is our QH. And during the isothermal compression, that's our QC. And we can plug those in and get those values. The thing missing is, so we can find all of this if we only knew the starting pressure or volume or ending for the isothermal expansion.
So I guess we just the starting property first states. The property at
Mhm.
any given state.
Uh-huh. Yeah, at any state, if we knew pressure or volume, then then that's the one thing we need to unravel all of this.
We can only do it in terms of like variables.
You also need to know the mass. Yeah, so that mass would, I guess, have to stay in there. Well, that problem's sort of a mess. Sorry about that. I think there are 2 bits of information missing, and then also I didn't I didn't tell you what a Carnot cycle is, so sorry about that. Any other? Were all the problems like that? I hope not.
I think one was easy.
Okay.
The first one, yeah.
Okay.
That was the first.
Any other questions about any of the other ones? Class is over. Ay, ay, ay. What a class.
5 minutes.
Mama said there'd be days like this. I thought she was a filthy, stinking liar, but she was right.
Teaching is not easy.
Okay, well, that's it. Goodbye. Oh, remember there's a quiz on Friday. And remember there's no school tomorrow. We do have class on Wednesday, but there's no school tomorrow because of Veterans Day.
Oh, Veterans Day.
Yeah.
What is the Carnot thingy going to be on it?
No.
No. Are we gonna learn it on Wednesday though?
Really, what I said today was about as much as I'm going to talk about it.
To be covered like a future class in engineering, like a total.
Yeah, maybe. I, you know, you